Scientists just uncovered something unusual happening beneath California's San Andreas Fault, and humans had been missing it for years. Using highly sensitive underground sensors and machine learning, researchers detected dozens of slow, silent movements that produced little or no noticeable shaking. Even more fascinating, some of these silent slips were followed by tiny, deep earthquakes. Does this mean the big one is coming? Not necessarily, but the discovery is changing what scientists understand about how faults actually behave, and it could reveal hidden patterns beneath other major fault zones around the world. In this video, we break down what silent earthquakes are, how machines found them, why Parkfield is so important, and what this discovery really means for California. San Andreas Fault, Baratasha earthquake, Doruahana, California, for earthquake science, or science, or geology, or earthquake news, or machine learning, or natural disasters. Big one. San Andreas Fault, San Andreas earthquake, California earthquake, big one California, silent earthquake, slow slip earthquake, slow slip events, earthquake science, earthquake prediction, California fault, Parkfield earthquake, machine learning earthquake, geology, seismic activity, earthquake warning, tectonic plates, natural disasters, California earthquake risk. The San Andreas Fault just did something scientists have never seen before, and it's alarming. There's a place in California where the ground can move without anyone feeling it. No violent shaking, no windows rattling, no walls cracking, no warning siren. The land simply creeps, almost invisibly, while life above continues as normal. Scientists have discovered that the fault does not simply sit still and then suddenly snap. It has another way of moving, a hidden behavior that can unfold over hours or days, and because it happens so slowly, humans can miss it completely. Now, researchers are using machines to search through years of underground measurements and uncover movements that were hiding in plain sight. The strange part is not simply that these silent slips exist. Scientists already knew slow movement was possible. The real surprise is how often they may be happening, and what appears to happen around the fault afterward. That raises a much bigger question. Could these invisible movements help scientists understand what happens before, during, and after major earthquakes? To understand why that question matters, we first need to understand the enormous machine beneath California. The San Andreas Fault marks a huge portion of that boundary. It stretches roughly 750 miles through California, cutting across landscapes that contain cities, farms, highways, mountains, and millions of homes. And the two plates are not moving directly toward each other, they are sliding sideways. That sounds simple until you realize how much energy is involved. The plates move only around a couple of inches per year in many places. That is slow enough to be almost meaningless to a person standing on the ground. You cannot watch it happen. You cannot feel it happening. But the movement never completely stops. Imagine two enormous rough blocks being pushed past each other. If their surfaces were perfectly smooth, they could slide continuously. But real rock is irregular. Parts catch, parts lock. Some sections creep, while others remain stuck. That is where the danger begins. Even when a section of the fault is locked, the tectonic plates around it continue moving. The surrounding rock slowly deforms as it stores energy. Think about bending a wooden ruler. At first, nothing dramatic happens. You apply pressure, the ruler bends slightly, and it holds. Keep pushing. And more energy becomes stored in the bent material. Eventually, if the pressure continues, the ruler snaps back. An earthquake is obviously far more complicated than a ruler, but the basic idea is useful. A locked fault can store strain for decades or centuries before releasing some of it suddenly. 2 inches sounds tiny, but multiply that movement by 100 years, and you get more than 16 feet of relative motion. That is movement the plates are trying to make while parts of the fault resist it. When a large locked section finally ruptures, the stored strain can be released rapidly. The ground on opposite sides of the fault can shift several feet in a matter of seconds. That is when the invisible process becomes violently visible. California has experienced this before. In 1906, a huge earthquake ruptured a long section of the San Andreas near San Francisco. The shaking destroyed buildings and infrastructure, but the disaster became even worse when fires erupted across the city. Broken water lines made firefighting difficult. Gas lines and damaged buildings created new hazards. Fires spread through neighborhoods for days. Thousands of people died, and much of San Francisco was left devastated. Then there was the enormous 1857 earthquake in Southern California. Much of the region was sparsely populated at the time, which meant the human toll was far lower than it might have been today. But the physical evidence showed just how powerful the fault could be. More recently, in 1989, the Loma Prieta earthquake struck during the World Series. Millions of people were watching television when the broadcast suddenly shook. Freeways collapsed, bridges were damaged, 63 people died, and that earthquake was not the hypothetical big one. That history is why scientists pay so much attention to the San Andreas. They are not studying an imaginary threat. They are studying a system that has repeatedly demonstrated its ability to produce enormous earthquakes. But there is something important missing from the simple story of locked fault, rising pressure, and sudden rupture. A fault can also move slowly, very slowly. Instead of releasing accumulated movement in a few seconds, a section can slip gradually over hours, days, or sometimes longer. The movement can be so gentle that it produces little or no ordinary seismic shaking. Scientists call these events slow slips or silent earthquakes. The phrase sounds contradictory. How can an earthquake happen without the shaking? The easiest way to understand it is to imagine pushing a heavy piece of furniture. If you shove it suddenly, it jerks, scrapes, and makes noise. That is similar to the sudden movement of a conventional earthquake. But if you lean against it and push with constant pressure, it may slowly slide across the floor. The object still moves. The energy is still being transferred. But the movement is spread out over a much longer period. That is roughly what makes slow slip so fascinating. The fault moves, but it does not necessarily produce the violent waves that announce an ordinary earthquake. And that creates a huge detection problem. Earthquake scientists have instruments designed to detect ground motion. Seismometers are incredibly sensitive, but they are optimized for vibrations and seismic waves. A slow slip can be different. Its movement may be too gradual to stand out as a conventional earthquake. So researchers need another way to see it. This is where specialized underground instruments become important. At carefully monitored sites, scientists can measure extremely small changes in how the ground is being squeezed, stretched, or deformed. These instruments are so sensitive that they can detect tiny movements caused by forces that would be completely invisible to humans. Even the ocean can leave a measurable fingerprint. As tides rise and fall, the enormous mass of water changes the forces acting on the Earth's crust. The ground responds by an incredibly small amount, and sensitive instruments can detect that response. Now imagine trying to find an even smaller signal hidden inside all of that. That is the challenge scientists faced at Parkfield, California. Parkfield is a small community along the San Andreas, surrounded by rolling hills and ranch country. It does not look like the center of a global scientific experiment, but beneath it is one of the most closely monitored sections of fault on Earth. Scientists have installed networks of instruments there for decades because Parkfield behaves differently from some of the locked sections farther away. Instead of remaining stuck for extremely long periods, parts of the fault around Parkfield can creep and produce repeated small movements. That makes the area an extraordinary natural laboratory. Researchers can watch the fault behave in relatively small ways and compare those observations with what they know about more dangerous locked sections. But there was a problem. The sensors were producing enormous amounts of data, but data is not automatically knowledge. Every day, underground instruments record tiny changes caused by tides, weather, groundwater temperature, surface activity, and countless other effects. Somewhere inside all of that information, the signal from a slow slip can be buried beneath layers of noise. Imagine a piece of paper covered with thousands of random scribbles. Somewhere underneath those scribbles is one incredibly thin pencil line, and your job is to trace that line without being distracted by everything else. A human can try, but when you have years of recordings, the task becomes exhausting, repetitive, and incredibly difficult. This is where machine learning changes the story. Instead of asking researchers to manually inspect every tiny fluctuation, scientists can train a computer system to recognize patterns. The idea is similar to recognizing a familiar voice in a crowded room. You do not consciously analyze every individual sound around you. Your brain notices a pattern, filters out the background noise, and identifies the person speaking. Researchers wanted a machine to do something similar with the underground data. They fed it years of measurements from Parkfield and asked it to search for the subtle signatures associated with slow movement. The computer did not get tired, lose concentration, or become overwhelmed after staring at the same graphs for hours. It could scan enormous amounts of information and search for combinations of signals that humans might easily overlook. And then it started finding them. Again and again, the system identified slow slip events buried inside the historical data. The result was striking. The machine found around 90 previously identifiable silent slip events in the Parkfield records, including more than 20 that had not been recognized during earlier human analysis. Think about what that actually means. The movements were not suddenly created by the algorithm. They had already happened. The sensors had already recorded them. The information had already been sitting there for years. The difference was that nobody had been able to reliably separate the important signal from the enormous amount of surrounding noise. The machine was effectively giving scientists a new pair of ears for listening to the fault. But researchers did not simply trust the computer. That would have been a dangerous mistake. A machine can find patterns that are real, but it can also discover patterns that only appear meaningful when they are actually random. So scientists compared the newly identified events with independent measurements from other instruments. For many of the detected slips, different instruments showed corresponding changes at approximately the same times. That independent agreement strengthened the case that the computer was identifying genuine geological events rather than simply hallucinating patterns inside random data. And that is where the discovery became even more interesting. Researchers began asking what happened around the fault immediately after these slow slips. A pattern started to emerge. Following some silent slip events, scientists observed an increase in tiny earthquakes deep underground. These were not the kind of earthquakes that send people running into the streets. They were extremely small, often far too weak for anyone standing at the surface to feel. But their timing mattered. A slow slip would occur, and then nearby, the number of tiny seismic events would increase. That suggested the slow movement was not completely isolated. It was changing something around it. Imagine a glass filled almost to the rim with water. If the glass is only half full, you can tap the table and probably nothing happens. But if the glass is filled right to the edge, even a small disturbance can send water spilling over. Scientists are not saying the San Andreas works exactly like a glass of water. The analogy is simply useful for understanding the idea of stress. A section of rock can already be under significant pressure and stress. A small movement nearby can alter that balance. That does not mean the movement will trigger a major earthquake. In fact, most slow slips probably do not produce anything catastrophic at all. But it does mean that different sections of a fault are not necessarily completely independent. They can interact. One movement can influence the conditions around another section, and those connections may be much more complicated than scientists once imagined. And that is one of the most important lessons from this research. For a long time, the simplest picture of an earthquake fault was almost binary: locked, then broken. But nature does not always follow such simple rules. Between those two extremes are countless smaller processes, including gradual movement, tiny earthquakes, changes in pressure, shifting stresses, and subtle deformation. The machine learning discovery is helping researchers see some of those processes more clearly. That does not mean scientists can now predict the next major earthquake. They cannot. Finding slow slips is not the same as discovering a countdown clock hidden beneath California. It does not mean California is about to experience a massive earthquake tomorrow, next month, or next year. Earthquake prediction remains one of the hardest problems in geophysics. Scientists still cannot reliably determine the exact time, location, and magnitude of a major earthquake before it happens, but better observation can still save lives. The more scientists understand how faults behave, the better they can estimate hazards, improve building standards, strengthen infrastructure, and develop more effective warning systems. And that matters because the biggest protection against an earthquake is not knowing the exact date it will happen. It is being prepared before the shaking begins. California has spent decades learning from previous disasters. Bridges have been strengthened, older buildings have been retrofitted, and hospitals and schools have been upgraded. Building codes have also become more demanding as engineers and scientists have learned more about the forces earthquakes can produce. There are also earthquake early warning systems designed to detect an earthquake after it begins and provide alerts before the strongest shaking reaches some locations. The warning may be incredibly short, but short does not mean useless. Even a few seconds can make a meaningful difference when people know what to do. A few seconds can allow a train to slow down. It can give someone time to move away from a dangerous window or heavy object. It can allow a person to drop, cover, and hold on. In a hospital, equipment can be secured and procedures can be paused. In a classroom, students can get underneath desks before the strongest shaking arrives. Those seconds are possible because scientists have spent decades learning how earthquakes move through the earth. And the same scientific mindset behind those systems is now being pushed further by machine learning. Instead of simply collecting more information, researchers are developing better ways to interpret the information they already have. The most fascinating part of this story may not even be the San Andreas itself. It may be what happens next. If a computer can search decades of geological records and discover events humans missed, researchers can potentially apply the same approach to other faults around the world. There are enormous archives of seismic, GPS, strain, and geological data waiting to be analyzed. Some of those records contain information that nobody has had the time, tools, or methods to fully understand. There could be slow movements beneath other regions that scientists have not yet recognized. There could also be subtle relationships between tiny earthquakes and larger fault movements that have been hiding inside old datasets for years. Patterns that were almost impossible for a human researcher to identify manually could become much easier to detect when powerful algorithms can process enormous amounts of information simultaneously. But the technology does not magically reveal the future. It cannot look at a graph and tell scientists exactly when the next major earthquake will strike. What it can do is help researchers ask better questions about the past and understand the present with greater precision. And that is the real breakthrough. The San Andreas has not suddenly become more dangerous because scientists discovered these silent slips. The fault has always been moving. The difference is that our ability to notice that movement has improved. For more than a century, people have feared the earthquake that might one day strike California. Now scientists are learning that the fault has a far more complicated personality than anyone could see from the surface. It creeps, it locks, it releases tiny amounts of energy, it produces small earthquakes, it stores enormous strain. And sometimes it moves so quietly that only an extremely sensitive instrument combined with a powerful computer can tell us that it happened. That should not make you panic. It should make you curious, because every hidden slip discovered in the data represents one more piece of a puzzle that scientists have been trying to solve for generations. Maybe one day those pieces will help researchers recognize conditions that make certain earthquakes more likely. Maybe they will improve hazard forecasts. Maybe they will reveal relationships between slow movement and seismic activity that scientists have not even imagined yet. But for now, the honest answer is much simpler. The machine has not predicted the big one. It has not produced a countdown. It has not given scientists a secret warning date for California. What it has done is give researchers a better way to listen. And beneath California, the Earth has been whispering for a very long time. We are finally getting better at hearing it.